heating curves and calculations with heating curves. So just a reminder that we have taken these heating curves from phase diagrams. And a phase diagram is where I'm looking at the pressure and the temperature, and it can be degrees Celsius or Kelvin, it doesn't matter. And I'm seeing for each individual substance what the pressure and temperature combinations that will give each state of matter. So phase diagrams are very helpful in that they can tell me for any substance what state of matter something will be in, as well as what the pressure or temperature change needs to be to get to that. So for example, if I'm in a liquid at a particular temperature and I would like to get to the gas phase, I can either increase the temperature or decrease the pressure to a certain amount. It also tells us what temperatures at different pressures you will have the state changes. So this line right here will be the state change from solid to liquid, and this line right here from liquid to gas. Here's sublimation from solid to gas. So what you realize is that for any state change, that state change will occur at a very specific temperature and pressure combination. So if I change the pressure, the temperature required to make that state change will also occur. So a concept that we now can introduce is that the concept of boiling point or melting point is the temperature at which the state change can occur at that given pressure, atmospheric pressure. So what it also means is that in order to go from a solid to a liquid, I have to go through that entire state change. So depending on my substance, if I have a lot of solid, then it will take a longer time in order for everything to become a liquid, and only after that state change has occurred can my temperature increase. Similarly, if I'm at a liquid state and I'm going to become a gas, I have to go through a state change. That entire state change occurs at this given temperature and pressure, and the temperature of my substance can't increase until all of the molecules have gone through that state change. So one thing that a phase diagram can't tell us is how much time and energy it takes in order to go through that state change. Now we know that it's related to intermolecular forces of attraction, and we talked about how intermolecular forces of attraction can alter this generic phase diagram. If I have stronger forces, it will tend to shift over to the right and down, and if I have weaker ones, then they'll shift to the left and up. So a useful tool is something called a heating curve. So a heating curve occurs at a particular pressure. So it's specific to a particular pressure, and it tells us the energy or time cost, right? Assuming that I'm inputting my energy at a constant rate, energy is also a stand-in for how much time it will take. So as I'm going through this, right now I've pegged this at 1 atmosphere pressure. So this is my heating curve. When I start at this very low temperature, right here and here, as I increase the temperature, I am increasing the temperature and my substance is in the solid state for that entire temperature change. So here, I'm increasing the temperature is in the solid state for the entire temperature change. When I hit this line segment here on the phase diagram, which is the melting, I can see now on my graph that the temperature is not changing, but that it's taking a certain amount of energy in order to melt. Right? So the length of the line segment is proportional to the amount of time that it will take to go through that state change. Once I've gone through that entire state change and all of the molecules are in the next state, now the temperature of my substance can increase. And so as I add energy, that will go into increasing the kinetic energy of my substance, right here. And all of this is in the liquid phase right here and right here as well. Then when I hit this line again, I'm now in another state change, that of boiling, going from liquid to gas. And again, the temperature remains constant, in this case at 100 degrees Celsius. So for that entire time, my Y value does not change. It's a flat horizontal line. And you can see by the length of this line segment that it takes a certain amount of energy in order to make that state change. And only after every molecule has gone through that state change can I then become in the gaseous phase and start increasing the temperature again. So if I raise the temperature and go through 3 states of matter, including 2 state changes, those are 5 different inputs of energy. Now, an interesting thing is that when you look at your heating curve, the line segment going from liquid to gas will always be longer than the line segment for melting. And again, that's because remember that our solids have to have maximum intermolecular forces of attraction, and our gases have to have absolutely none. Liquids are somewhere in between. So as a result, it will take more energy to overcome all of the remaining IMFs, because the bar is so high, to become a gas, than it does to simply overcome some of them enough to move in a liquid state. Also, the slope of this line, remember, is going to be not as steep because it's going to take a huge amount of energy. It's going to take a huge amount of energy in order to overcome all of the remaining IMFs. So this line will always be much longer. And in the liquid, it's going to have this more shallow slope because it takes more energy to not just heat up the liquid, because the energy that it takes to move this will not necessarily translate to this, but I'm also overcoming some IMFs. Remember that liquids become less viscous as I heat them up. So it's going to mean that as I'm going through this increasing temperature of my liquid, I'm not just transmitting kinetic energy, but I'm also increasing my ability to overcome IMFs. So if I'm going to do calculations off of this, I need to first sketch my heating curve, and I have to highlight the temperature range that I'm going to be using. So an example here, 300 grams of water is heated at a constant pressure of 1 atmosphere. When the temperature increases from -10 to 85 degrees Celsius, calculate the energy required. So I'm going to sketch my generic heating curve for water, and it's at 1 atmosphere pressure, so I know my benchmarks are 100 degrees Celsius and 0 degrees Celsius, is where the melting point and the boiling point are. And then I basically put in my values for my word problem, -10 and 85, and highlight the portions of that heating curve that I'm actually using. So although the heating curve has 5 line segments, I'm only using 3 of the line segments and not even all of the liquid line segment or the solid line segment. Each line segment is a separate calculation. So in this, I have 3 line segments highlighted. One of them is a state change, and there are 2 temperature changes. I know it's a temperature change because there is a change in Y that is not 0. Anytime I have a temperature change, the amount of energy required is going to be multiplied by the mass times the specific heat times the change in temperature. Now, it's dependent on mass, because if I have to raise the temperature of a cup of water versus a whole pot of water, the whole pot of water will require more energy. So certainly as the mass increases, the energy that was required to do that will increase. It also is dependent on the specific heat. That's that heat inertia of my substance. So water has a high specific heat, so it takes more energy to raise a certain amount of that substance the same amount of temperature. We talked about the difference between a hot summer day in which the water temperature is still very cool, but the sand is very hot. Same energy is coming from the sun, but because the specific heat of the sand is so much less, the sun's energy can raise the temperature of that much, much more quickly. And finally, the amount of energy that it takes depends on how much I'm trying to increase the temperature, right? If I'm just trying to warm something up a little bit, that won't take as much energy as if I'm trying to really heat it up an amount. So that's whenever I have a temperature change, because I have a delta T. If I have a state change, then the energy required is going to be equal to mass times the heat of reaction. In this case, the heat of the state change is my heat of reaction. So again, it's a mass dependent property. If I have to melt more like a big iceberg versus a small ice cube, it will take more energy. Similarly, if I have to boil it, that will take more energy than if I simply have to melt it. So again, one state change, so I'm going to use E times M heat of state change, and 2 temperature changes, and I'll use E equals MC delta T. It's important to remember that whenever you have a temperature change in 2 different states of matter, you cannot use the same C value, right? The specific heat for ice is always going to be lower than the specific heat for water. so you can't do that. Also, oftentimes the temperature changes aren't going to be the same. So my calculations go as this. For the temperature change, first temperature change is when I'm taking my solid from -10 to 0 degrees Celsius. That's my delta T. The specific heat for ice will be given, and that's a constant, 0.5 calories per gram per degree Celsius. And the mass was given in the problem as 300 grams. For my liquid, I'm taking my liquid from 0 to 85 degrees Celsius. That's my delta T, right? 0 to 85. The specific heat is 1 calorie per gram per degree Celsius, but it's the same mass. In the state change, right here, heat of fusion, again, is going to be a standard thing that will be given to you. And the mass still hasn't changed. It's going to be 300. So I have all of the things that I need to make my calculations. I now plug and chug. So this first part where I'm increasing the temperature of my solid will be MC delta T because I'm changing the temperature. So 300 times 0.5 times 10 is 1,500 calories. In order to make this increase the temperature of the liquid, it will be MC delta T again. So 300 times 1 times 85 equals 25,500 calories. And then I have to remember that in order to increase the temperature of the liquid, I had to have a state change. So I have to multiply the mass times the heat of fusion, which is 300 times 80, and I get 24,000 calories. When I add these all up together, the total energy it takes is 51,000 calories, or 51 kilocalories. So classic mistakes. Classic mistake is to use just one equation, E equals MC delta T, where I plug in the mass of 300, and I do the delta T from -10 to 85, and I don't know which C that you'd be choosing, and just assume that it's just the same thing. So there's two mistakes with that. One, each state of matter has a different C, and I use a lot of energy. In fact, 24,000, almost the most amount of energy, going through the state change from solid to liquid. So if I neglected this and I simply did the temperature changes, I would be grossly underestimating the amount of energy it would take in order to take 300 grams up from -10 to 85 degrees Celsius. So the bottom line is, when you're doing any sort of calorimetry calculations that require a heating curve, you first sketch the heating curve, then you put in the values of what temperature it changes states of matter. You put in the temperatures of what your word problem encompasses, and then you highlight the regions of the graph that are applicable to your word problem. And for every line segment, that's a separate calculation. So if you have 3 line segments that are highlighted, that's 3 separate calculations. And you have to make sure that if there's a state change, that you include mass times the state change, heat of fusion or heat of vaporization. And remember that the specific heats of the different states of matter will differ within a substance.